How was your test?
It was good.
How much did you get in physics? Ellen, how much did you get in the last test?
I didn't get the marks yet.
Hanifa?
Yes.
Sorry?
We didn't get the marks yet.
Not audible. Maimuna, how much did you get in the last test?
Sir, I didn't attend it.
Okay, today we will start with semiconductors. This is the last. Now, semiconductors. What do you mean by how do we differentiate semiconductors, metals, and insulators? Alan, what do you mean by metals? In case of metals, semiconductors, how will you distinguish between the conductors, insulators, and semiconductors on the basis of conductivity or resistivity? Resistivity of insulators is maximum. Resistivity of conductors is minimum. Resistivity of semiconductors lie between metals and insulators. Now, very easy chapter. These are semiconductors. This is the this conduction band, this valence band, this is energy gap. So energy gap is less than 3 electron volt. Fine. Now this is energy band diagram for semiconductor. This is conduction band, this is valence band, this is fine. So energy gap is less than 3 electron volt. There are two types of semiconductors, intrinsic and extrinsic. Intrinsic semiconductors are pure semiconductors. Intrinsic semiconductors are pure semiconductor. Extrinsic semiconductors are impure semiconductor. Intrinsic semiconductor, the electron density and hole density. What do you mean by hole, Alan?
So can you repeat the question?
What do you mean by hole?
So it's the pockets formed in a semiconductor.
Sorry? Sorry, could you repeat, please? This topic is very easy. Today I'll teach you whatever you have did in class 12. Okay, Mahamuna, what do you mean by hole? If you tell me wrong, then it's fine. I'll make it correct. But please let me know. Anipa, what do you mean by hole? There are two types of semiconductors. Absence of electron in area. Okay, good. It means the electron area. Okay. Now there are two types of semiconductor, intrinsic semiconductor and extrinsic semiconductor. Intrinsic semiconductors are pure semiconductors in which electron density and hole density. Hole density, electron density means the number of electrons per unit volume or the number of holes per unit volume. So let it be a place. This place. Initially, let it be an electron placed on some area. If it leaves its place, a vacancy is created, positively charged. So that is known as hole. Electron vacant places are known as holes. Holes don't move, but they seem they are moving. Fine. So intrinsic semiconductor electron density per unit volume and electron density, that is electron density equals to hole density. It means the number of electrons per unit volume equals to number of holes per unit volume. Now mathematically, Ne, this represents the number of electrons, electron density, number of NH, the holes density, and Ni, initial concentration. Fine. So intrinsic concentration charge carrier concentration. At equilibrium, what happens? The number of electrons equals the number of holes. So this is the pair of regeneration, rate of regeneration. Sorry. At equilibrium, the rate of regeneration, whether it is intrinsic semiconductor or extrinsic semiconductor, the rate of combination regeneration always remains same. So Ne multiply means electron density multiply by hole density equals to Ni square. Total current in semiconductor is due to electron plus due to hole. So total current equals to summation of the current due to current plus due to electron plus the total current due to hole. Example, silicon and germanium. Fine. Okay, silicon, what is the valency of silicon? How many electrons? Alan, what is the valency? Alan, please could you let me know what is the valency of silicon? How many valence electrons in the outermost shell? Mamuna,
So 4.
4. Okay. Silicon is taken, silicon or germanium. They are semiconductor. Now, extrinsic semiconductor. What happens in extrinsic semiconductor? We have to do with the means we have to do the impure pure semiconductor, intrinsic semiconductor with the elements from the element trivalent and pentavalent. Fine. To increase the conductivity of pure semiconductor. That there are two types, N-type semiconductor and P-type semiconductor. So N-type semiconductor known as donor type. Fine. We do with the use of pentavalent impurities. For example, phosphorus, arsenic. Fine. Electron density. In this case, the number of electron increases. In case of N-type semiconductor, number of electrons means the electron density greater than the hole density. Fine. So current due to electron will be greater than the current due to hole. But overall, the semiconductor remains neutral. Now conductivity is Ne mu E. This is mobility. This is electron. This is electron density. This is a energy band diagram. Now this is 0.01 electron volt. This is conduction band. This is donor impurity. This is energy gap. At temperature greater than 0 Kelvin. You should remember the band diagram. That's it. Now P-type semiconductor. P-type semiconductors. These type of semiconductors are known as acceptor type. Doping with the trivalent impurity like aluminum, gallium, or indium. What is the valency? How many electrons are balanced in the outermost shell? Mamuna, in case of aluminum. Alan, Saifullah, anyone?
3.
3. Fine. Electrically neutral. Conductivity is NH, means that in this the number of holes is greater than number of electrons and hole current is greater than electron current. In this case, now this is energy band diagram. This is conduction band. This is valence band. Energy gap. Energy gap decreased by 0.1 to 0.06 electron volt. Now, try this question, write your answer in chat box fast. The chapter is very easy. Tomorrow we will discuss transistor and logic gates. Okay, try this question fast and write your answer in chat box. Fast everyone, write your answer in chat box. Hey Farhat. Hey. Okay, fine. So for p-type semiconductor, which of the following statement is true? Holes are majority charge carriers and electrons are minority charge carriers. 2D. Okay. Just a minute. Sorry. Now, do the second one. Write your answer in chat box, everyone. Done, everyone. Write your answer in chat box fast. Hanifa A. An intrinsic semiconductor converted into n-time extrinsic semiconductor fast. Saifullah, Farhat, Hanifa, Heba. Hanifa, I think she has written the answer. Okay, Heba, Mamuna, write your answer in chat box. Phosphorus is the answer. Here is the answer. Here is the answer. These are the two words. Okay. In n-type semiconductor, are you listening? Everyone, am I audible to everyone? In n-type semiconductor, which charge carriers are in majority? Holes or electrons?
Electrons.
Which semiconductor is known as p-type? This semiconductor is known as acceptor type, p-type or n-type? Just a minute. Mamuna,
Yes, sir.
in which type of semiconductor is known as acceptor type? Fast. Mamuna, fast. Am I audible to a Mamuna? Please, you should respond whether it is correct or wrong.
Intrinsic semiconductor.
Alan, what's the answer? Which semiconductor is known as acceptor type? Which semiconductor is known as acceptor type?
Sand type.
And type. Saifullah, Hanifa, anyone?
P type.
P type. Okay, P type is known as acceptor type. If I dope any of the pure semiconductor, will its neutrality change?
Yes.
Neutrality. Overall charge. If I dope any of the pure semiconductor, will its neutrality change? No. It remains as it is. Give 2 examples of intrinsic semiconductor. Saifullah,
Sir, can you repeat?
give 2 examples of pure semiconductor, intrinsic semiconductor.
Silicon, germanium.
Carbon has also leave it. Just a minute. Let me ask some question. This chapter is completely theory based. Let's proceed. Now PN junction. What is PN junction? Let it be a semiconductor. Half it is doped with P type and half it is doped with N type semiconductor. Now what happens? There is a process. As we do the doping, the process starts. Now from P type semiconductor, what is the majority charge carriers in P type? Saifullah, what are the majority charge carriers in P type?
Holes.
Holes.
If
In P-type semiconductor, the majority charge carriers are holes, whereas in N-type semiconductor, majority charge carriers are electrons. So what happens? PN junction. So if let it be a pure semiconductor, if we do half of P-type and rest of half with N-type semiconductor, means half of trivalent and rest of half with pentavalent. Now, in majority charge in P-type semiconductor, the majority charge carriers holes, whereas minority charge carriers are electrons. In N-type semiconductor, majority charge carriers are electrons, and minority charge carriers are holes. Now, the majority charge carriers of P-type the majority charge carriers of P start going from P to N side, whereas the majority charge carriers of N side, holes, electrons, start going from N to P side. Now there is a diffusion of the holes with the electrons. The diffusion of holes with the electron starts, and there is a current due to this diffusion. That current is known as diffusion current. Now what happens if the holes leave their places from P type? then electron will be created. This side will be negative. If the electrons leave their places, then this side will be positively charged. Now electric field is formed from N to P side. Now no more majority charge carriers either of P type or N type will be able to cross this barrier. This is known as potential barrier. Now this is negatively charged as the holes leave their places. Now the negative charge is induced on the P side, and as the electrons leave their places, the positive charges are created on the N type. Fine. Next, positive charges are created on the N side. Now there is a distance between these two charges. Now electric field is created from N to P side. Now no more majority charge carriers are able to cross this electric or potential barrier. Now the minority charge carriers of N side holes, minority charge carriers in N-type semiconductors are holes, and in P-type electrons. Now electrons are able to cross this potential barrier because electric field will support the minority charge carriers to cross this potential barrier, whereas in case of this, the holes are positively charged, and if we place the positive charge in electric field, so they will experience the force in the same direction of the electric field. Now they are able to cross this electric field. Now there is a drifting of minority charge carriers due to which a small current is created. That current is known as drift current. All right. Now this is known as depletion layer. Now what happens in depletion layer? The region on either side of the junction, this region, either side of the junction, this region is free from mobile charge carriers. It means there are no charges, there are no mobile charges within this region. They are just neutral atoms. That's why this is known as depletion layer. All right, Alan.
Yes, sir.
Or shall I repeat the entire thing again? Mamuna, shall I repeat the entire thing again? Hanifa, am I audible?
Yes, sir.
Saifullah, did you get it? Or
Yes, sir.
shall I repeat?
It's clear, sir.
Okay. A brief. Now, what is PN junction? This is known as junction. Fine. Now, this is a junction. This is P-type semiconductor. This is a P region and N region. Now, if we take a pure semiconductor, let it be silicon or germanium, let it be. So if we take a pure semiconductor and if we do half of by trivalent and the rest of by pentavalent. Pentavalent means N-type and trivalent means P region, means P-type semiconductor. So what we do half of the semiconductor with the help of pentavalent and half of the semiconductor with the help of trivalent. Now what happens? The process starts going. As we start doping, the process starts going. Now the majority charge carriers of P-type semiconductor holes, they start moving from N to P, from P to N. And the majority charge carriers of N side electrons, they start going from N to P region. It means there is a diffusion of the current. There is a diffusion of the electrons with the holes. Now there is a diffusion process starts. So the current starts flowing from N to P region. Sorry, the current starts from P to N region. That current is known as diffusion current because the direction of the current electron is from N to P. Fine. Now, if the electrons which are majority charge carriers in N-type semiconductor, if they leave their places, then the positive charges are accumulated on the N side, and as the holes leave their spaces, then the negative charges are induced on the P side. Now there is a positive charges induced on the N side and the negative charges are induced on the P side. Then there is a distance between the two charges. So E equals to V over D. Now the electric field is created from N to P region. Now no more majority charge carrier either from P side or N side are able to cross this depletion layer, this potential barrier, because this is the potential, this is positive sign, this is negative charge, this is known as potential barrier. So no more majority charge carriers are able to cross this potential barrier. Now further, what happens, the minority charge carriers of n side and minority charge carriers of p side. Now minority charge carriers in n side are holes. Now holes are positively charged, so they are able to cross this potential barrier, because electric field will support the holes to move p side. Now electrons from p, minority charge carriers, are able to move from p to n side. Now there is a differing of minority charge carriers, then due to which a current is induced, a current is formed in the semiconductor. That is that current is known as drift current. Now the current due to majority charge carriers is known as diffusion current, and the current due to minority charge carriers is known as drift current. Now this is depletion layer. A depletion layer means the region which is free from the mobile charge carriers, known as depletion layer. So depletion layer, the region on either side of the junction which becomes depleted free from the mobile charge carriers, is known as depletion layer. Now order depletion layer is 10⁻⁻⁶. Meter. Now different currents, diffusion current from p to n side, and drift current from n to p side. Steady state, what happens, diffusion current equals to drift current, and this is diffusion current, this drift current in steady state. So net current in the semiconductor becomes 0. And this PN junction diode, a diode is forming. Now this is a symbol of PN junction diode. This is positive, this is p type, this is n side, this is n type semiconductor. This is a symbol how to use it. This is p, this donates, this portion donates p, and this donates n. This is anode, this is cathode. Now biasing, there are two types of biasing. Biasing means the connecting an external battery or EMF to a PN junction diode. There are two types of biasing: forward biasing and reverse biasing. In forward biasing, we have to join positive to p side and negative to n side, and current goes from p to n. Fine. In case of forward biasing, it behaves like a conductor. It means depletion layer. Basically, depletion layer is a kind of resistance in semiconductor. Fine. So depletion layer shrinks. Depletion layer shrinks in case of forward biasing. This is the IV characteristic for forward biasing. This is knee voltage. So in case of forward biasing, diffusion current is greater than drift current, and depletion layer shrinks. It means the resistance is minimum. In case of reverse biasing, positive is connected to the N and negative is connected to the P. In case of this, the small current flows. That current is known as leakage current or reverse current due to the minority charge carrier. So in this drift current is only due to the minority charge carrier, whereas the diffusion current is due to the majority charge carriers. Now try this question and write your answer in chat box. Fast. B, D. Alan, write your answer. Farhat, D. Now, out of the following, which one is forward bias? Now, what do you mean by N? And in case of forward bias, the positive is connected, means the P is connected to the higher potential and N is connected to the lower potential. Fine. It's not about positive and negative. D. Which of the following is forward bias? Which is higher potential? In my 4 options. This is P side and this is N side. All right. This is -4. -4 or -2, which is greater? Saifullah, which is greater? -4 or -2?
-2.
So it is reverse bias. This is -2, this is +2. Okay. D. D is the correct option. 0 is greater than -3. Now try this question and write your answer in chat box fast. Fast, write your answer in chat box, everyone.
Sir, is the potential 0 over there?
Which question? Second. The given circuit. There are 2 diodes are given.
No, the potential, is it 0?
Okay, just a minute. Let me tell you. This is 10. This is 10. Sorry. 10 volt. Now write your answer in chat box, everyone fast. Hanifa, Alan, Mamuna, write your answer in chat box fast. Now write your answer, everyone. Saifullah A. Alan, what happened to you? Write your answer. Mamuna, write your answer. Hiba. Aksha, write your answer. Aksha, write your answer, everyone. Fast, please write your answer. Now, how to do? Now, this diode is in reverse bias because N is connected to the higher potential and P is connected to the lower potential. So, reverse bias. This is forward bias. So, it will permit the current to pass through it. Now, I equals to, just a minute. So, I equals to V over total R. So total R will be 4. Now 2.5 amperes. Is it fine? Is it clear to everyone?
Yes, sir.
Now dynamic resistance. This is IV characteristic. This is forward bias characteristic. This is reverse bias characteristic. Now this is Zener voltage. Zener voltage. Zener voltage. This is Avalanche breakdown. Now Zener voltage. Now this is forward bias, new voltage. Now what happens? Characteristic means basically we study the nature of the current. We study the nature of the current versus voltage. Now this is a knee voltage. This is the voltage at which the current starts growing. Now in case of reverse wide, the current after this is reverse volt. This is reverse current. This is forward current. This is forward voltage. This is reverse voltage. And in case of forward wise, gradually at some point, up to some point, the current becomes zero, and after the knee voltage, the current start growing. Fine. In case of reverse wise, just remember one thing: in forward wise, the current should be measured in milliamperes. In case of reverse wise, the current should be measured in microamperes. This is reverse voltage. This is now Zener voltage is that voltage at which the voltage remains constant, but the current increases tremendously. All right. Now this is the voltage at which the current increases tremendously. Now, Alan, what is the difference between N-type semiconductor and P-type semiconductor? What is the difference between P-type semiconductor and N-type semiconductor? Mamuna, Saifullah, what is the difference between N-type semiconductor and P-type semiconductor?
N-type have a more number of electrons, whereas P have a more number of holes.
Alan, by which element we have to do to get N-type semiconductor, trivalent or
So
pentavalent?
for N-type, use pentavalent, and for P-type, use trivalent.
Okay. Which semiconductor is known as donut type, Mamuna? Which semiconductor is known as donut type? Mamuna, Aksha. This type of semiconductor is known as donut type.
P-type.
And Alan, which type of semiconductor is known as donut type?
Sand type.
N type. What is depletion layer? Hanifa? What is depletion layer? What's the depletion layer? Hanifa, what's depletion layer?
When the charge decreases, the layer and the electrode charges decrease.
Your voice is not clear. Okay, Saifullah, what is depletion layer?
There be a collection of positive and negative charge particles in between.
No, the region in junction diode free from the mobile charge carriers. Alan, what is diffusion current? What is diffusion current, Alan?
So is it the current caused by the change in
The current
caused by the change in transfer of electrons? I'm not sure about that one.
No, the current due to the majority charge carriers, while the formation of junction diode. All right. What is drift current? Saifullah, what is drift current? Hiba, Farhat, what is drift current?
The movement of minority charge carriers.
From which region to which region? From N to P or P to N?
From P to N.
From P to N. No, from N to P. Just a minute. N to P. Now, what is the direction of diffusion current from N to P or P to N? Hiba, what is the direction of diffusion current from N to P or P to N? Farhat, Hanifa, Aksha,
N to P.
N to P. Diffusion current. Look. Now in P-type semiconductor, majority charge carriers are holes, and holes are positively charged. All right. And holes are positively charged. So what is the conventional direction of current? The direction of the positive charges. Fine. So in majority charge carriers, while the formation of the depletion layer, the majority charge carrier, it means the holes in case of P-type semiconductor and electrons in case of N-type semiconductor. Now there is a diffusion process goes on while the formation of depletion layer. So electron moves from P to N and electrons move from N to P. So there is a diffusion current due to the majority charge carriers. So what is the direction of holes? From P to N. It means the diffusion current, the direction of diffusion current is from P to N. Now minority charge carriers. Minority charge carriers. Sorry, just a minute. So there is an electric field found between the depletion layer. Now in an N-type semiconductor, minority charge carriers are holes, and in P-type semiconductor, minority charge carriers are electrons. So holes go from N-type semiconductor from N to P region. So the direction of drift current will be N to P. P to N diffusion current and N to P drift current. All right, drift current. So the direction of diffusion current from P to N and drift current from diffusion current from P to N and drift current from N to P. Okay. The barrier potential question. The barrier potential of PN junction diode depends on the type of semiconductor material, amount of doping or temperature. All are correct. I repeat myself, the barrier potential of PN junction depends on the nature of the semiconductor, amount of doping, or third is temperature. Please, all three, just type of semiconductor, not on the temperature, not on the amount of doping. Which of the options or option is correct? All three, any of two, or just single? Saifullah, please, everyone, listen.
Sir, can you repeat, sir?
Okay, the barrier potential of PN junction depend on the temperature, amount of doping, and the nature of semiconductor. First,
Amount of doping and its nature.
nature. Alan, Hanifa, Hiba. All three. Okay. All three. Amount of substance, nature of semiconductor, and the amount of doping. Temperature also. Okay. If I increase the doping, how does it affect the depletion layer? If I increase the doping, if I increase the level of concentration of doping, how does it affect the depletion layer? Depletion layer gets shrink or spread out if I increase the doping. Fast. If I increase the doping, how does it affect the depletion layer? Decreases. All right, not increases. Depletion layer gets decreases. Fine. And just remember, if I increase the concentration, depletion layer decreases, hence the electric field increases. Because E equals to V over D. All right. In case of forward biasing, Saifullah, how do you connect junction diode with the battery?
Positive to P and negative to N.
Good. Alan,
Yes, sir.
in case of reverse biasing, how would you connect the junction diode with the battery?
So positive N type and negative to P type.
Positive to N type, negative to P type. Okay. Higher potential to the N type and lower potential to the P type. Now, this is half wave rectifier. What is rectifier, by the way?
It converts DC to AC.
AC to DC. Okay. What is the principle of rectifier? What is the principle of rectifier? So rectifier is a device which converts AC to DC. Now principle base, if the junction diode is forward biased, then it behaves like a conductor. That means it permits the current. If it is reverse biased, it doesn't allow the current to pass through it. Okay, now this is a transformer, this is a AC source. This is the point A. So in forward bias, if positive, in case of positive half cycle, this junction diode behaves like a forward bias and it permits the current and we'll get across the load. Fine. This is the waveform. This is known as waveform. waveform. So for positive half cycle, we get some output. This is load. For negative half cycle, so for the negative half cycle, for the negative cycle, it means if this and becomes positive, so this diode will be in reverse bias, so it doesn't allow the current to pass through it. So for every positive cycle, we get output across the load. Now full wave rectifier, there are two junction diodes when this is transformer. So for the positive half cycle, the voltage at A means if it A is higher potential, so this diode will be in forward bias. And for the negative half cycle, this diode will be in forward bias. And this is waveform. So for both the cycles, we get output across the load. This is the graph. This alternating current sinusoidal. We have to calculate the fundamental and the ripple. Ripple is 2 times of frequency. Fast. Write your answer in chat box. I just come in a minute. B. B is the answer. So 2 times of frequency, 100 Hz. Right. Okay. Saifullah, what is the principle of half wave rectifier? What is the principle of rectifier?
Forward diode.
What? Forward diode?
Positive to P and negative to N.
Okay. There is a question. Let me ask you. Carbon and silicon both have same lattice structure. All right. In the outermost shell, there are 7 free electrons. Sorry, everyone. So I was asking a question. Silicon and carbon both have same lattice structure, having 4 bonding electrons in each. However, C is insulator, whereas silicon is intrinsic semiconductor. Why? The option is, in case of carbon, the valence bond is not completely filled at absolute zero temperature. In case of carbon, the conduction band is partially filled even at the absolute zero. The fourth bonding electrons in case of carbon in the second orbit, whereas in case of silicon, they are in the first, in the third. Which of the option is correct? I repeat, carbon and silicon both have same lattice structure, having bonding electrons in each. However, C is insulator, whereas silicon is intrinsic semiconductor. Three options I'm giving you. In case of carbon, the valence bond is not completely filled at absolute zero temperature. In case of carbon, second option, in case of carbon, the conduction band is partially filled even at the absolute temperature. In case of it, the third option, the fourth bonding electrons in case of carbon is in the second orbit, whereas in case of silicon, they lie in the third. Which of the option? First, please write your answer. Everyone, please write your answer. There are 4 valence electrons in the outermost shell in both the elements, but still we consider silicon as a semiconductor and carbon as an insulator. First, Shaifullah, Alan, Mamuna, Farhat, write your answer. Please write your answer. See. Rest of you write your answer fast. Please, everyone. Alan, which of the option is correct? In both the elements, there are 4 valence electrons in the outermost shell, but still we consider the silicon as a semiconductor, whereas the carbon is an insulator. But why? Fast, please write your answer in chat box. Everyone, please. Please write your answer. Alan, am I audible to you? Please, at least everyone should respond.
Yes, sir.
Now, which of the option is correct? Silicon and germanium both have 4 valence electrons in the outermost shell, but still we consider the carbon as an insulator and silicon as semiconductor. But why? Which of the option is correct? I gave you 3 options. Shall I repeat myself?
Yes, sir.
Now, first is, in case of carbon, the valence bond is completely filled. Is not completely filled at the absolute temperature. In case of carbon, the conduction band is partially filled even at absolute temperature. Or the third option is, the 4 bonding electrons in case of carbon is in the second orbit, whereas in silicon they lie in the third orbit. Which of the option? Third. Farhat, am I audible?
Yes, sir.
Which of the option is correct? Maimuna, which of the option is correct? Heba, which of the option is correct? Hanifa, Aksha, which of the option is correct? Which of the option is correct? Very easy question. Third option is correct. Light emitting diode. Now this light emitting diode converts. It is forward bias, converts biasing electrical energy into light energy. This is the symbol. Now photodiode detecting optical signals, reverse bias. This is the symbol. This is the graph for photodiode. If we increase the intensity, the current increases automatically. Photoelectric effect. Fine. If we increase the intensity, current increases, but is in reverse bias. Just remember one more thing. It is always connected in reverse bias because the fractional change in minority charge carriers is dominating over the majority charge carriers. All right. Because the fractional change in minority charge carriers is dominating over majority charge carriers. All right. This is solar cell.
Sir, can you scroll up?
Okay.
So what is after carriers?
Just a minute. What did you say?
After carriers, change in minority charge carriers.
Is dominating over majority charge carriers.
Done, sir.
Okay, now solar cell. It converts solar energy into electrical energy. All right, so it converts solar energy into electrical energy. This is a symbol. No, this is the graph for solar cell. Now xenon diode is always connected in reverse bias. And this heavily doped. One thing also. Heavily doped also. When operated in breakdown region, means when the current increases tremendously. This is a symbol used as a voltage regulator. Try this question. Fast, everyone, please. Alan, write your answer. Farhat, Heva, Mehmuna, please write your answer. Good. Mehmuna, please write your answer. C. Okay. Next. Now try this question. This one. And write your answer in chat box. Fast. This is VI characteristic. Write your answer in chat box. Once you do. Once you have done, please write your answer. The question is very easy, all right. A. A. Rest of you write your answer, please. Eva, Hanifa, Aksha. Mamuna, did you write the answer, Mamuna? Okay. Farhat. A. Now try this question. Next. Write your answer. Now, a PN photodiode, that is PN junction diode, is fabricated from a semiconductor with a band gap. Energy gap is given 2.5 electron volt. It can detect a signal of wavelength. E equals to SC over lambda. You have to apply and write your answer fast. This formula we have to use it. Please write your answer in chat box. Please write your answer. What is H? 6.6 10 to the power minus 34. What is C? 3 into 10 to the power 8. Lambda we have to calculate. So lambda equals to 6.6 into 10 to the power minus 34. 3 into 10 to the power 8 over what is E? 2.5 electron volt. This means 0.6 10 to the power minus 19. Please write. What is the possible value? If you calculate it, how much will you get? D. Alan, what is the answer if I solve it?
Sir, I'm getting 4.95.
4.95 meters.
4.95 into 10 to the power minus 7.
4.95 10 to the power minus
7.
7 meters. Now,
Yes.
the answer is given in Armstrong. Now, if we switch it, let it be round off 5. So 5,000 into 10 to the power minus 10 meters, that is 5,000 Armstrong. Now to detect must be less than this. D. So the signal of wavelength can be detected by the photodiode. Is it clear?
Yes, sir.
Mamuna, which semiconductor is donor type? N type or P type?
N-type.
Okay. Farhat, what is the principle of rectifier?
It converts AC to DC.
Principle. I'm asking principle. Saifullah, what is the principle of semiconductor? Saifullah, what is the principle of what is the principle of rectifier?
Positive to P type and negative to N type.
No, this is not the principle. When the diode is in forward bias, it permits the current, whereas in reverse bias, it doesn't permit the current. All right.
Yes, sir.
LED is in reverse bias or forward bias? Alan,
Yes, sir.
LED is in, look, how do we connect the junction diode to get LED, light emitting diode? Forward bias or reverse bias?
So forward.
Forward. Okay. Just a minute. Okay. Now in semiconductor at room temperature, the valence band is partially empty and conduction band is partially filled in semiconductor at room temperature. Okay, so the valence band is partially empty and the conduction band is partially filled. The valence band is completely filled and the conduction band is partially filled. The valence band is completely filled and the conduction band is completely empty. Which of the option is correct? I repeat, in semiconductor at room temperature, Okay. So the valence band is partially empty and the conduction band is partially filled. The valence band is completely filled and the conduction band is partially filled. The valence band is completely filled and the conduction band is completely empty. Which of the option? One. Good. So in semiconductor, room temperature. One. Just remember, at room temperature in semiconductor, the valence band is partially empty and conduction band is partially filled. The barrier potential of a PN. Okay. If the junction diode is forward bias, will it increase depletion layer or decrease? If the junction diode is in forward bias, so how does it affect the depletion layer? Depletion layer will get increased or decreased. Fast. Everyone, please.
Sir, can you repeat?
If the junction diode is in forward bias, so how does it affect the depletion layer? Depletion layer will increase or decrease? Great, degrees. Now, again, the barrier potential of PN junction diode does not depend on temperature, doping, diode design, or temperature, or forward bias. The barrier potential of PN junction diode doesn't depend on which parameter: forward bias, doping density, diode design, or temperature. Which of the option is correct? Fast. Diode design. Fine. So it does not depend on the diode design. In forward bias, the width of depletion layer. Depletion layer consists of: one, electrons; second, protons; third, mobile charge carriers; and the immobile ions. Which of the option? Depletion layer consists of electrons, protons, mobile charge carriers, and immobile ions. Which of the option is correct? Fast, please. Very easy.
Does not consist of.
Okay. Depletion layer consists of immobile charge ions. Okay. Okay, fine. Last. In photodiode, what kind of biasing we use? In case of photodiode, what kind of biasing we use? Forward or reverse? Saifullah,
Sir, can you repeat?
in case of photodiode, which kind of biasing we use? Forward or reverse?
Reverse.
Reverse. Why do we use reverse biasing in photodiode? Because fractional changes in minority charge carriers dominating over majority charge carriers. In solar cell, which kind of biasing we use? Alan? Anyone? In solar cell, which kind of biasing we use?
Forward.
Forward. Anyone else? Farhat? Mamuna, Heba, which kind of biasing we use in solar cell? Anyone? Saifullah?
Forward.
No biasing is used. All right. Let me tell you one more thing. In case of solar cell, fine, there is a finger type electrode, okay, is used. This finger electrode is the nature of it. Finger type electrode is metal. All right. Why do we use it? Because the flow of electrons in semiconductor is much less than the metals. All right. That's why we use finger type electrode in solar cell. Okay, that's it. Okay, tomorrow we will discuss the junction transit and logic gates. Bye.